Okay, so what we are doing now is we're going to make a transition to much more to phase 3 of this class, which is once we have all our data, maybe we've presented our data, how can we do calculations and analyze our data? So from now on, for the most part, we're going to be assuming that we have quantitative data, and we'll be doing calculations with this data. So the first thing that we need to do is I need to give you some background information in order for you to understand the sorts of things that we'll be talking about. And so that topic is probability. So we're going to talk a little bit about probability. All right. So as we do this discussion, you can imagine, if you like, that we have some collection of data. For example, did a survey and got people's heights. Okay. So some variable takes on different values, and those different values are our data. So you can imagine, for example, if we did a survey and let's say I got one person's height was 68 inches, 70 inches, 71 inches. As mathematicians, we think of that as saying, for the first person, x equals 68. Then for the second person, x equals 70. For the third person, x equals 71. So as we've said all along, x represents our data values. That x has a name. It's called a random variable. Now we could be talking about discrete or continuous data, although we'll usually be talking about about continuous data. But in that case, you have a discrete random variable or you have a continuous random variable. Now, another change. Previously, we talked about frequencies and relative frequencies. From here on out, we're nearly going to banish those terms, and what we used to call relative frequency is now called probability. So in the discrete case where you are able to count things, we can think of probability in exactly the same way. It's the frequency divided by the total number, and the notation for that is f divided by n. So before, we would say we could write a chart representing a frequency distribution. We don't call it that anymore. What do we call it now? Yes, probability distribution. Okay. So all the things that we said before apply once again when we're talking about probabilities. So for example, any probability value has to be from 0 to 1. If a probability equals 0, that's the same as something never happening. For example, 0 out of 12. And if probability equals 1, it always happens. And the total probability is 1. Now, we more frequently talked about, or we sometimes talked about things in terms of percents. We also talk about these values in terms of fractions and also in terms of decimals. From here on out, as I just said, we'll be doing lots and lots of calculations. Now, what we said is that fractions are good for an immediate representation. Percentages are good for talking about things in common language. But when we're doing calculations, writing it as a decimal number is the most useful way. So since we're going to be doing lots and lots of calculations, that's the way we'll typically be writing things down. So you should get used to writing it down as a decimal number. As a decimal number, the total probability is 1. Okay. So now a little bit about the notation of how we write these things down. Suppose we want to talk about the probability that a student's age is over 100. First of all, how do we just write that? Before we answer the question, how do we write that down? What does P stand for? Probability, absolutely. Okay. So, x, in general, not in this problem, but in general, what does x represent? In general, it represents a dated value. And in this case, the dated value represents the student or the student's age. So, if we read this off quite literally, this says the probability that the student's age is greater than 100. So this translation, I think, is fairly straightforward. Okay. Now, by the way, in this class, what is the probability that a student's age is over 100? Right. Is anyone here over 100? No. Okay. So it's 0. Next, we can ask about the probability that a student's age is between 0 and 100. So, how are we going to write this down? Well, there's a little trick to writing between statements, and they look like this. So, first of all, a nice little trick to help you with this is that for between statements, you literally write the x between the two numbers. So, first of all, that's helpful. But also, let's keep in mind, what is the relationship between x and 100 here? It's less than. What's the relationship between x and 0? What's less than what? Right. So, and we would say that x is, relative to 100, greater than. So this is the same as saying that x is greater than 0 and less than 100. That's the same as saying x is between 0 and 100. That's why we write it like this. So this, you can read this as x, the probability that x is between 0 and 100. And by the way, what is that probability for this class? It's 1. And again, you could think of it as, got about 21 students today. You could think of this as 21 over 21, but of course, that's just 1. Okay. Next. What about the probability that a student's age is 25? How would we write that? P x equals 25. It's the probability that x equals 25. Okay. Just notation. Now, just a little refresher, how do we know that, what are the important characteristics of a probability distribution, at least when we're talking about discrete values? Well, is this a probability distribution? How can we check what should be true? Right. So that's I like to say that's the second thing. The first thing is what should be true about all the probability values. Well, okay. Yes. Also, every individual value should be somewhere from 0 to 1. So is that true? Is that true? Yes. The other thing we have to check is, do they add to 1? And do they add to 1? Do the probabilities add to 1? No, they don't. Okay. They actually add to 1.2. So this is not a probability distribution. Because in this case, we're saying the total probability is 1.2, which is like 120%. That doesn't make any sense. Right. So what about this table? Does this represent the probability distribution? So the first value has a probability of 0.37. The first value, which is the next value, which is 2, has a probability of 0.19. The next value, which is 3, has a probability of 0.21, and the next value, which is 4, has a probability of 0.23. So first of all, does it satisfy the first condition? All the values from 0 to 1? Yes. Next thing we have to check is, do they all add to 1? So, do they? Calculator. Yes, they do. So this represents a probability distribution. Now we can draw a picture to represent this. Now what do we used to call a picture where we drew it and it was represented the values and all those things? A histogram, exactly. We used to call it a frequency histogram. No more. What do we call it now? A probability histogram. And it just looks almost exact. It looks exactly the same.
How did you get the probability?
I made them up.
And the values?
I made them up. Okay. So now we're going to do our first fancy calculation. So using this probability distribution, I'm going to ask, what's the mean? Now typically when we calculate the mean, what do we do? Right. Add them up and divide by how many we have. Exactly. So if you were to do if you try to do this in a naive way, you would say, well, I've got values 1, 2, 3, and 4, so let me just add them up and divide by 4. But is that the right thing to do? It is not. Because if you just add them up and divide by 4, what you're basically saying is that each of them happens one time, or they happen with equal likelihood, as if you were rolling a die. But is that what this chart tells us? No. So the question is, how do we adjust our calculation of the mean in order to represent that fact? Absolutely. We talked about this a little while ago. It's the exact same calculation as for a weighted mean. So let me pull up, here we go. So if you think back to this calculation, what we did was, actually, yeah, this one's good. We're using as our data values 15, 25, 35, 45, 55, if you remember this example with the ages. And notice that what we don't do is just add up those values and divide by 5. What did we have to do? We had to say, well, the 15 occurs once, 25 occurs 7 times, and that is when you get this expression. Okay. And then we add them all up and we divide it by 12 because 12 was the total number. But there's another way to think about this. Break this up into individual fractions. So we have 15 times 1 over 12 plus 25 times 7 over 12. Break it up into individual fractions and it looks like this. But now, for 15, what is 1/12? One-twelfth is not the frequency, it's the relative frequency. But we don't say relative frequency anymore. What do we say? Probability. Exactly. So writing down the calculation in this way gives us the mean, exactly the same thing, only we can think of it differently. In each case, we take 15, which is our data value, and multiply it by 1/12, which is our probability. And then you add them all up.
And you get the same answer.
And you get exactly the same answer. So the thing is, by doing this, you would say, well, I'm adding stuff up, but we're so trained to think that when we calculate the mean, you have to divide by something. But we've already divided. Where is it that we've already divided? It's in the probability. We've already divided. So all you need to do is multiply by the probabilities and add them together. And the dividing has already happened inside there. So let's apply that to our current example. Oops. Nope. Okay. So, how do we find the mean? And so, remember the notation for mean is mu. So how do we find the mean?
0.37.
Okay. And what do we do with 0.37?
Times 1.
Right. So the first thing is 1 times the probability plus 2 times 0.19 plus, and then you just keep going. Exactly. Do we need to divide? We've already divided. Where is the already divided? It's in the probability. If it helps, when the probability is 0.37, if it helps, think of that as 37 out of 100. So the divided is already contained in there. So let's work this out. 1 times 0.37 plus 2 times 0.19 plus 3 times 0.21 plus 4 times 0.23. So the mean is 2.3. Now, a mean of a random variable is also called its expected value. Now, in general, I see no need to give the same thing lots and lots of different names, but I'll present you with 1 or 2 problems that sort of give an idea of why the name expected value sometimes makes sense. We're going to play a game. This is a game where you roll a die. If you roll a 6, you win $5. Otherwise, you lose $1. So, in math, I would say, what's the expected value of this game? Another question we can ask about this game is, would you play this game? So, would you play this game? Okay. So, well, whether or not you would play this game, I imagine probably depends on whether you think you're going to win money or lose money playing this game. So the thing we have to figure out is, if you play this game, say over and over, are you going to win money or lose money? And that's exactly what we want to figure out right here. So, how can we write this out in a mathematical way to calculate the answer to that question? When you play this game, what can happen? You can win or lose. Now, what is the value of winning? $5. What is the value of losing? It's not 1. It's sort of like 1, but not quite. It's what? It is -1. Because you're losing. So, now the question is, at this point do I say, well, sometimes you win, sometimes you lose, so the average is 5 minus 1 over 2? Is that the right thing to say? No, why not? Yeah, because you lose more than you win. So we just can't take the average of those two numbers directly. So the way we figure this out is we also need to include in our calculation what's the probability. So what is the probability of winning? Sorry? 1 out of 6, right? And what's the probability of losing? 5 out of 6. There you go. I'm sorry? In this case, I'll leave it as a fraction because the calculation is easier with the fractions. Yeah. Okay. So now, how do we find the value of this game? Exactly. Well, this is the mean or the expected value, and the notation for expected value is E of x. So x represents our data, and E just represents expected value. So you said I have to multiply. What do I multiply? And what do I have to do with these things? Have to add them together, exactly. So this works out to 5/6 minus 5/6, 0. So what does that mean? You break even. Now I want to support this calculation with some intuition. Suppose we play this game and you roll 1, 2, 3, 4, 5, 6. What happens? When you roll a 1, lose $1. Roll a 2, lose $1. Lose $1, lose $1, lose $1. But then what happens? You roll a 6, you win $5, and it cancels out, and you're back at square one. Okay. So these are two different ways of thinking about this problem. One is the calculation, and the other one is we're sort of counting it out in a way that makes sense. So the reason why having the calculation approach is helpful is because sometimes the numbers might not work out so nicely. Let's play this game. Let's flip cards. When you pull a king from the deck, you win $10. For everything else, you lose $1. What's the expected value? So first of all, would you play this game? No, why not? Yeah, there's only 4 kings, but you win $10. Okay. So most people are saying no. Let's actually do the calculation and see how it works out. So first of all, I want to make sure everybody knows what's a deck of cards. All right.
And then how many kings are there? 4?
There are 52 cards. There are 4 each of ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. And each of these is called a rank. Next, there are 13 each of the spade, heart, diamond, club. Each of those is called a suit. So, for example, what are the 4 kings? Each king. What are each of the kings? Exactly. King of spades, king of hearts, king of diamonds, king of clubs. Okay. So, for example, if I said, what's the probability that you pull an 8 of spades?
4 out of 52.
8 of spades. There's only one 8 of spades. So it's 1 out of 52. Okay. What's the probability that you pull a heart? A heart.
13 out of 52.
Right. So there are 2 ways to think of it. You could either say it's 13 out of 52 because there's 13 hearts out of 52 cards, or you can just very simply say it's 1 out of 4. 13 out of 52 reduces to 1 over 4. Same thing. Okay. So now that I'm moderately confident that you know, okay. And let me just say also that we will from time to time do problems using a deck of cards. So this is always true about a deck of cards
But how was
for
the
this
8
class.
of spades 1 out of 52?
How many 8 of spades
I
are
thought you
there?
said there was 4 of each.
There are 4 eights.
Oh.
So there's an 8 of spades, an 8 of hearts, 8 of clubs, 8 of diamonds. So there's only one 8 of spades. All right. So let's figure out what's going on in this game. So what's the first thing we should write down? Outcome. So what are the outcomes? Win or lose. Value of winning is 10. Value of losing is -1. And what are the probabilities? And let me just say, I'll usually write down just prob for probability. Right. Yeah, how many ways are there to win? What's the probability of winning? 4 out of 52. And what's the probability of losing? If 4 cards win, how many cards lose? 48. There's 48 left. Yeah? Okay. So now, let's figure out the expected value for this game. How do we do that? Right. What do we multiply? Okay. So you work that out and you get 40 over 52 minus 48 over 52, which gives you -8 over 52. And let's calculate what is -8 over 52. There we go. -0.1538. So what does that mean? No, it means you lose. What do you lose? Yes, thank you, Bovie. You lose 15 cents on average. Because what is this a measure of? We said when we win $10. When we lose $1. What happens on average? Negative means we're losing 0.15. That's not bananas. What is that? That's dollars and cents. So this is -0.15 we lose about 15 cents, and that's on average. So should we play this game? No. Alright. Now, a quick question. Does this mean that if you play the game one time, you're going to lose 15 cents? Can that ever happen? You can never play one time and lose 15 cents. That's not what this is describing. What this is describing is that if you play this game, one way to think of this is that if you play this game over and over forever, on average you'll lose 15 cents for each time that you play. That's one way to think of this. In the same way, for example, you hear people say the average American family has 2.3 kids. Does that mean that there's a family somewhere that has 2.3 kids? I hope not. That would be painful. Okay, so it's exactly the same idea. Alright. There's another way to think of this. What happens when you play through the entire deck? How much money would you win?
40.
You win $40, exactly. 4 kings, $10 each, you win $40. But how much do you lose? You lose $48, $1 for each of the other cards.
So you lose more money. You're gonna lose more money than you're gonna win.
Exactly. How much more? but how much do you lose for each trip? You win 40, you lose 48. So you lose $8 on every trip through the deck. But a trip through the deck is how many cards? 52. So you lose $8 per 52 cards. 8 divided by 52. That's another way to think about it. 8 divided by 52? Negative 0.15. Okay. So again, this is another way to think about it. All right. Okay. So let me just say that these are the basics of probability. We're going to come back later later in the course, later this semester, and do probability in some more serious depth. But these are the basics for what we need to go forward. Any questions? Okay, next thing.